Uh, Good afternoon to everyone. First, I would like to thank the organizers for giving me this opportunity. As LK said, I am talking about efforts and current status of Electron-ION Collider Indian group. So this is the outline of my talk. I'll talk about the little history about EIC India initiation and introduction to the Electron-ION Collider. After that, I will discuss a few highlights of previous efforts from the Indian groups in EIC software. Basically, we participated in the Athena software benchmarking. Then I will show some efforts towards the EPIC simulation, which is currently ongoing, and possible detector hardware projects in which we are interested in EIC, and future directions, and finally I will summarize. So moving to the first part, so this is a little history in Indian context. So our first formal interaction with EIC was in December 2015 at this workshop in IIT Kanpur, and we had a dedicated session of heavy ion and QCD. And in that session, we had a half-day discussion on EIC. So that was the first introduction to the heavy ion community to the EIC. Then, after some gap, there was a first full-fledged discussion, which happened in this QCD with Electron-ION Collider meeting in January at IIT Bombay. And you can see we had one-to-one interaction in that meeting with the Indian groups from the EIC members from abroad. So a few outcomes of that meeting was one of our master student from Punjab University. She started working in the EIC S-Phoenix based simulation, and would like to thank Christine for helping out in this simulation project. And then another major breakthrough was we started a bi-weekly meeting within the Indian group, and we formed a EIC India mailing list. And I would like to encourage those who are not involved and who are interested to please write to us. We can include you in this discussion. And as you can see, this QIC is now a regular assignment within India. Our second meeting was held at the IIT Delhi in December 2022, and this is the third meeting in the series which you are all enjoying here. So coming to the EIC India group, so this list shows current council members for the EPIC collaboration. About 17 groups are there, which are basically from India. These are the council members of EPIC, and this includes both theory and the experimental groups. And in addition, we have few more groups which are not the current council members, but still they are part of EIC India. And as you can see from this map, all this list covers approximately full region of India. So that's very interesting and important. And also, if you can see this bar chart, after US, the number of institutions in EPIC, the largest number is from the Indian groups. So that is also one of the major workforce from here in India. Then talking about the expertise, so most of the groups from here, they are from the either heavy ion or particle physics experiments. They have experiences at INO, COSI, KEK, RIC, LSC, and FAIR. And the expertise include the physics analysis, simulation, detector hardware, etc. In detector hardware and all other projects hardware related, we have been involved in the DCS, trigger, electronics, grid computing. And then in various experiments, we have been involved in various detectors such as photon multiplicity detector, which is completely an indigenous detector made within India. Time projection chamber, GEM, focal, CRU, muon spectrometer. In STAR, we have again PMD, HFT, CBM, we are muon chamber. CMS, we have a few detectors which are contributed by the Indian group. And in terms of physics analysis, you can talk about different physics. All are covered within the group, fluctuations, correlations, light flavor, nuclei production, resonance, strangeness, jet physics, heavy flavor physics, UPC, etc. And also we have strong simulation people here doing detector and physics simulations. So this is star PMD detector. This is star Alice PMD detector. This is CMS outer hadronic calorimeter, muon spectrometer in Alice. So since our getting together, we have been, as a group, we have been participating in various EIC activities. As you know, there was a collaboration formed as Athena. So most of us, we were in the Athena collaboration. And we participated in the Athena EOI preparation, its review and submission. We also participated in other activities such as logo design competition, and we have been participating in various surveys related to EIC, and majorly we have contributed in the EIC software, basically benchmarking of various software related to Athena, Athena detector. In addition, we have held various important responsibilities within the EIC collaboration, such as international representative for steering committee, diversity, equity and inclusion committee, elections nominating committee, integration committee, bylaws and charter committee, EPIC membership committee, etc. So in 2022, the two detectors, Athena and the HA, they resulted to a new collaboration called EPIC collaboration, Electron-Proton-Ion Collider. Now we are participating in this as a group from India. So this is little detail about the Electron-Ion Collider. You also heard a lot of details in LK's talk. So this is a new innovative large-scale particle accelerator facility which is planned at the Brookhaven National Laboratory. It's the highest priority project which is appeared in 2015 as well as in 2023 US Nuclear Physics Long Range Plan. It has been favorably endorsed by a committee established by the National Academy of Sciences in 2018, and in 2019 it was granted CD0 status, which marked it as an official project of the US government. Then talking about the physics program, we have been listening a lot in this conference here. So basically it addresses three profound questions about nucleons and how they are assembled to form the nuclei of atoms, and such as how does the mass of the nucleon arise, how does the spin of the nucleon arise, and what are the emergent properties of dense system of gluons. So technically it's a high luminosity of the order of 10⁻34 per centimeter square per second, polarized electron-proton ion collider with center of mass energies ranging from 20 to 140 GeV. And as we have been talking about in this conference, this is only new collider in foreseeable future, and hence it will remain at frontier of accelerator and science and technology. So methodology, basically physics methodology includes the deep inelastic scattering of electron with proton and nucleus. It has an advantage such as a probe, electron beams provide unmatched precision for the electromagnetic interaction. It provides direct model independent determination of parton kinematics, and various terminology which are involved in these collision systems are listed here, and these important terms x, q square and s are related to this relation. Then the kinematics range of covered by EIC, the left plot is x versus q square. As you increase the center of mass energy, x decreases and hence also q increases, q square increases. So the range covered by EIC is shown here, and also the measurements or the regions covered by the other experiments. So one can see it has a wide range over x and q square, and on the right side you see x versus q, where EIC region is also compared with the future LHC experiments and the past experiments. So one can see it actually bridges the gap between the this LHC experiments as well as the previous experiments. And if I consider all these regions, then EIC plus other experiments almost cover full or maximum range of X and Q square, which provides us a comprehensive data set to do different types of physics. Then coming to the detector part, detector is the electron-proton-ion collider. The basic components are listed here: hadronic calorimeters, electromagnetic calorimeters, solenoid, tracking devices, and PID detectors. Overall detector requirement is very stringent based on the physics of EIC. We need large rapidity coverage, high precision, low mass tracking, electromagnetic and hadronic calorimeter having equal coverage of tracking, high performance PID to separate the basic particles, and to maximize the scientific flexibility, it will also include the streaming DAC, which is basically a triggerless data taking, and it will include the artificial intelligence and machine learning techniques. So all these stringent requirements push the technology to a higher limit in the EIC. So coming to the next part of my talk, which is basically highlights of some previous efforts done by the Indian groups towards the EIC software. So would like to mention that most of the works were done by the master students in various institutes. So they have been trained in this kind of software, and now I think most of them have moved to other places. Maybe some of them are in EIC also abroad. So, so this is what we started in 2020, I guess. In Punjab University, we had a master student which worked, and we worked in collaboration with Christine and Jane. And the task was to include a silicon tracker and new beam pipe to obtain momentum resolution for pion and electrons for different conditions. And the plot here shows the momentum resolution for pions and electrons for a given eta and momentum. The lower plot shows the resolution as a function of momentum resolution as a function of momentum for pion, and this is for electron track. Some of the observations were including silicon trackers improve momentum resolutions towards the higher eta, and if we include the constraint of truth vertex, that leads to better momentum resolution. And one can see from this plot that resolution for electron is worse than pion, which is due to the Bremsstrahlung radiation. So after that, the Athena collaboration was formed, and we worked on various software groups. For example, first was Fun for All simulation. Institutions involved were Punjab University and IIT Indore, and this work was done in collaboration with Chris and Kolya. The task was to obtain the energy resolution and parameterization of energy resolution using pions and electrons for electromagnetic and hadronic calorimeters. And this plot shows delta phi versus delta eta. You make a circular cut to do the manual clustering, and this is difference in tower energy to the generating energy as a function of generating energy to get the resolutions. So the plot here shows electron energy resolutions for central, forward and backward calorimeters, electromagnetic calorimeters, and this is representing the pion energy resolutions for electromagnetic and calorimeter, hadronic calorimeter combinations. So next was MC data validation. IIT Bombay, IIT Madras, Goa University. Now the PI has moved to IIT Bombay, Mandi from here. This work was done in collaboration with Marcus, and the task was to study global properties of hadronic final states in disk events and other interesting observables at EIC by using different event generators, and then compare these simulation outputs with the existing data and see if there are differences with respect to the models, so that one can tune the models accordingly. So the work was done using different models such as Pythia, Harving and Sherpa, and these are various topics in which people were involved. And I will just show a few example plots from here. Right side is D star production cross-section, Harvey compared with the existing data. J side production cross-section, Harvey compared with the existing data. And transverse energy flow for Harvey and Sherpa. Jet transverse energy for Pythia, comparison with the data for different jet algorithm methods. So these were the work being done during the time of Athena collaboration, which continued, but I think it was stopped later on because Athena was stopped and there was not much enthusiasm among the people, and students also maybe they went on to move to some other places. Okay, so the other work which was involved is Escalate. This is Ramakrishna College. This PI has also moved to IIT Mandi now and IIT Indore in collaboration with Dimitri. Escalate is basically a software to work full simulation of EIC. Both Python and C++ can be coded here, and it represents a complete package of root and GIA4. All are inbuilt. These are some validation plots, beam pipe construction, calorimetry using machine learning to separate electron and proton pion energy deposition. Okay, so then also we participated in EIC smearing. Basically, people from IIT Patna, Madras, and MNIT Jaipur and Central University of Karnataka were involved in collaboration with Kolya. Task was to study the smearing effect for the exclusive physics with EIC. This represents a workflow chart for their simulation. Basically, they generate the input MC event file for a given process, and then this is stored in a root format, and from there you apply a fast simulation with the EIC smear software and EIC smear detector scripts, and then smearing effect is observed or analyzed. So these are some example plots for a electron-proton collision at a certain energy for Q square, PT, W square, and upper plots represents the unsmeared particles and the lower plots represents the distributions after the smearing effect. In addition, people were also involved in this project East, which was headed by Makota SI. Then we had also contribution to the DAC group. Basically, Central University of Karnataka was involved in it. There is a crucial input to the DAC team. For example, if we know the background rates of each detector arising out of various sources, and this can be used for calculating data volumes and corresponding bandwidths, which can be used in the experiment. And the task was to calculate the photon rates of synchrotron radiation on various detectors. They used this simulation tool SynRed, which is well-established machine simulation tool to generate synchrotron radiation photons. They simulated two different setups with and without gold coating and then analyzed these photon and electron counts. And just would like to mention that these results were used in the Athena white paper to calculate maximum data volumes as shown in this table. Okay, so now I move to the next topic, which is our current efforts. Basically, we are doing some simulation in EPIC, and what are our future plans. So we are actually currently doing vertexing at EPIC. Two master students from Punjab universities are involved in it. Our task is to evaluate the vertexing algorithm performance of EPIC. The strategy is one of the students will do the few track simulation, check single track performances, resolution, efficiency, DCA at first at 0, 0 vertex and then move away from 0, 0 in XY direction. Another student is working on Pythia disk simulation starting from 0, 0 and then later on she will also move to away from 0, 0. So this is the basically simulation detail for few track simulation. Parameters are also listed here. And the lower plot shows the vertex resolution in our direction for 005 vertex. You can see we have a nice vertex resolution here. But as we move from away from 00, such as 500, this is XY 50, then you see some distortion, and as a quick fix, we are discussing that we need to recalculate the point of closest approach in the simulation, and this is work which is still ongoing. Then another student is working on this PTI simulation, which is the details are shown here. Basically, she has just calculated the vertex resolution as a function of number of reconstructed tracks for X, Y, and Z direction. And then a lower plot shows the projections with some fitting to the Gaussian distributions to calculate the widths. And this is also work which is just started and it is still in progress. So just want to mention that currently we are involved in a hardware project called the forward calorimeter at ALICE. It's a high granularity forward calorimeter to explore small X structure of nucleons and nuclei. And these are the main goals which are close to the EIC physics. And you can see this plot I have also shown. This region is covered by focal detector. These are the layers which are described here. And this is the prototype detector which was tested at PS CERN. And this is India ALICE focal test beam at PS CERN. So this is our current hardware project which we have some experience. So now I'll just point out about this. I think we will discuss today in today's meeting also. But just to mention that very preliminary discussions we have, possible hardware contribution in EIC. We will be interested in dual radiator ring imaging Cherenkov to measure particle identification, which will be using aerogel and silicon PMs. Also, we will be interested in forward electromagnetic calorimeter for energy measurements, use tungsten powder scintillating fiber and silicon PMs. Again, one of the project could be time of flight detectors for particle identification using AC LGAD. And there is an interest in contributing to the DAC. Basically, one can do data reduction using machine learning techniques on FPGA. In addition, Deepak is also interested in evaluating time synchronization feasibility among various subsystems and incorporating streaming readout in simulations. So more details are there in Shuddha's talk and Vedant's talk, but we will have also discussion on this in today's evening meeting and discussions. Okay, so this is just a very preliminary and tentative table of interest of various groups, what they want to do in EIC. You can see various institutes, they have listed their interests. Some of them are interested in the detector hardware projects. Some of them are interested in DAC, physics simulation, and all these things. But obviously, this is a very tentative list, and still discussions are ongoing on it, and we will hear more in the evening today. So talking about the facilities available, we have basically 4 places where we have lab facilities and other things available. At NISER, we have a clean room, RPC lab, silicon detector lab, and electronics gas mixing, as you can see here. BHU, you have a working lab, gas tight gem chamber, spectrophotometer, gas mixing, etc. IOP, which is also at Bhubaneswar, they have a working lab, clean room, gem testing, setup, electronics, etc. And Jammu, we have a working lab, a probe station to do the CV measurements and electronics, etc. But I would like to mention that some of the groups, they have a possibilities to extend the lab facilities. So these facilities can be extended to the other groups at other places in course of time. Okay, so this also Bedanga talk about, but I'll just mention here that EIC science has been included in the Indian long range plan. Basically, it's a mega science vision 2035 nuclear physics document, which is analog to the US long range plan. And it's a roadmap which has been prepared by the Indian nuclear physics community. The document is released by the Principal Scientific Advisor of Government of India in December 2023. And in this document, EIC is mentioned as one of the important mega science project in Indian context. And this gives us a favorable environment to get funding. And due to this, we are moving towards the funding application. What is ongoing is we are writing a detailed project report to be submitted to Indian funding agencies. Inputs are being collected from various participating institutes. If you have not sent your input and you are interested, you can contact. And we aim to finish this exercise within a couple of months. So we'll see how it goes. And with that, I would like to just summarize. Indian participation in EIC or EPIC is based on basically 4 different aspects. We have an experience at various facilities for detector hardware, simulation and analysis. We have contributed in the software, EIC software group already. We are finalizing options for a detector hardware project in EPIC. We are writing a detailed project report which is to be submitted to funding agency for funding. And with that, I would like to thank you for your attention. And I acknowledge EIC India group and EPIC collaboration. Thank you. And more we will hear in evening's discussion.
Thank you. So, do we have questions?
Where you were talking about the vertexing, do you have only one EP collision vertex in the event or more than one?
Actually, it is done in 2 scenarios. I can go there. So currently, let me show you. So we actually following this 2 things. One is we are doing field track simulation in which we are throwing 10 muon per event in flat theta pt. Okay.
So it's a muon gun and not a EP collision.
Yeah, it's a gun.
Okay.
And then we are also doing this Pythia disk simulation, which is the details are shown here. So this is using Pythia and then passing through the detector simulation.
Right. So in this PTA, you have only one EP vertex per event. Right. Okay.
Yes, yes, yeah.
And surely the vertex reconstruction will get smeared if you add additional vertices. But do you have that physics scenario in mind?
I don't get your question.
I think he asked for pileup. We don't have pileup in EIC.
Okay.
We have one DIS event every 200 bunches.
Okay.
The cross-section is so low that is a huge difference to the LHC, which has, of course, several events in one bunch crossing.
I mean, I come from an LHC background,
Exactly.
so my mind is
Oh,
pileup contaminated.
A very valid point.
Okay, thank you.
More questions? I think that was a very good talk to stimulate the discussion for later. So thank you very much, and then we move on.